Hi everyone! This video looks at an example of calculating the metal ion concentration and the percent metal ion remaining in solution in an EDTA titration after the equivalence point. An EDTA titration is a complexometric titration where a metal ion is titrated with EDTA to form a complex. When EDTA reacts with the metal ion, this is called a formation reaction. The fractional amount of the EDTA species that primarily reacts with the metal depends on the pH. Therefore, the resulting metal ion concentration will be pH dependent. Our goal with an EDTA titration is typically to react more than 99.9% of the metal ion, which correlates to leaving less than 0.1% in solution. For the complexation reaction, we're showing a generic notation for the metal ion as M, having a charge of X+. It reacts primarily with the deprotonated form of EDTA, noted as Y4-, to form a charged complex. For example, the species Y4- corresponds to the alpha fraction alpha 4, also known as alpha Y4-. If we know the pH of the reaction, we can use alpha and the analytical concentration of EDTA to obtain Y4-. This makes it easier to set up our calculations. In an EDTA titration, we have some volume of EDTA reacting with the metal ion, so we have to set up a millimole table. The E row of our millimole table tells us where we are on the titration curve and helps us to figure out the concentration of the metal ion. In this sample millimole table, we are looking at the E row. Here we see that the metal ion goes to 0 and the EDTA is in excess. This tells us that the reaction is beyond complete, that we have excess EDTA beyond what was necessary to complete the reaction stoichiometrically. This puts us in the region of the titration curve after the equivalence point. Here, the amounts of EDTA and the complex will influence the calculation of the metal ion concentration in solution. In this region, we have a different type of calculation than what we've typically seen. First, we will rearrange the K'F expression to solve for the metal ion molarity. We will need to plug in the millimoles of EDTA and millimoles of complex from the millimole table, and then either the calculated value of K'F or the value of Kf and the alpha value at the experiment pH. To determine if the reaction is complete, we calculate the percent of Mx plus remaining to see if it is less than 0.1%. We take the molarity of the metal ion remaining in solution and divide by the original molarity of the metal ion times 100. Here's our example. The first thing we do is set up our millimole table. Our reaction is our metal ion, Fe2+, reacting with EDTA to form the complex, which is FeY2-. The rows are ICE, initial, change, and end, and our units are millimoles. So we'll calculate our millimoles of Fe2+. We have 12 milliliters of solution times the molarity of the iron 2, which is 0.1007 moles of Fe2+ divided by liters of solution. The liters of solution will cancel, leaving us with milli and moles. For our sig figs, we have 4 sig figs in the volume, 4 sig figs in the molarity, so our millimoles will also be rounded to 4 sig figs. Doing the math, 12.00 times 0.1007 rounded to 4 sig figs gives us 1.208 millimoles of Fe2+. The millimoles of EDTA we get from the volume, 10.22 milliliters of solution, times its molarity, which is 0.1264 moles of EDTA per liter of solution. Liters of solution will cancel, leaving us millimoles. We have 4 sig figs in our volume, 4 sig figs in our molarity, and our millimoles will be rounded to 4 sig figs. Doing the math, 10.22 times 0.1264 rounded to 4 sig figs gives us 1.292 millimoles of EDTA. Entering these values into our millimole table, we have 1.208 for the iron, 1.292 for EDTA, and 0 for the complex. We subtract the smaller value from each reactant, which is 1.208. We subtract that from the iron and from the EDTA, and we add 1.208 to our complex. The iron goes to 0, the complex goes to 1.208, and the EDTA, we calculate 1.292 minus 1.208, rounded to 3 decimal places, because it's subtraction, gives us 0.084. Evaluating the E row, we have excess EDTA, excess titrant, which tells us we are after the equivalence point. We'll be using the mass action expression for our conditional formation constant K prime F. So let's just write that down. K prime F equals FeY2 minus divided by Fe2 plus times EDTA. And we're rearranging this to solve for the iron 2 plus molarity. So that will give us Fe2 plus equals the complex FeY2 minus divided by K prime F times the molarity of EDTA. So we need the information for K prime F. We can calculate that separately and then plug it into this expression, or we can incorporate alpha and Kf directly into this expression. If I go about it that way, then our Fe2 plus equals the complex FeY2 minus divided by Kf times alpha Y4 minus times EDTA. And even though we have the molarities shown here, we can actually plug in millimoles because the volume terms will cancel. So this is one of those rare occasions where we actually can plug millimoles into the equation. We'll get the same answer. So plugging everything in, we have 1.208 in our numerator divided by Kf, which is 2.0 times 10 to the 14 times alpha, 1.3 times 10 to the negative 2 times the millimoles of EDTA from our millimole table, 0.084. Checking our sig figs, we have 4 sig figs in the numerator, 2 for Kf, 2 for alpha, and 2 for the millimoles of EDTA. So we'll round this molarity to 2 sig figs. Doing the math, make sure you use parentheses in the denominator, we have 1.208 divided by parentheses 2.0 times 10 to the 14 times 1.3 times 10 to the negative 2 times 0.084, close that parentheses, equals 5.5 times 10 to the negative 12. And the units are molar, and the substance is Fe2+. We have one more calculation to do, and that is to determine if the reaction is complete. So we get that percentage from the molarity we just calculated, 5.5 times 10 to the negative 12, divided by the original molarity, 0.1007 molar, times 100. We have 2 sig figs in our numerator, 4 in the denominator. 100 is exact. This percentage will be rounded to 2 sig figs. Doing the math, 5.5 times 10 to the negative 12 divided by 0.1007 times 100 out to 2 sig figs gives us 5.5 times 10 to the negative 9%. And because our threshold is 0.1%, this is clearly a situation where the reaction is complete.